Hi, in this video we're going to start a new chapter. This chapter is on probability, and today we're going to look at one of the most foundational concept of that, which is likelihood. So in everyday language we tend to think of likelihood on a sort of scale from something impossible to happen, unlikely to happen, then likely to happen, and then something certain to happen. And in our mind, every day, we tend to categorize events based on where they lie on this line. It's a very natural thing for us to do. For example, the event, I will see the sun tomorrow. Now that is something that's fairly likely to happen. Even if the weather is bad, we are fairly likely to see the sun tomorrow. So that tends to go on the more likely end of the spectrum. Seeing snow tomorrow, however, that's a lot more unlikely, especially here in Wales. So I'm probably not going to see snow tomorrow, so that goes on the more unlikely end of the spectrum. Let's do a few more of these. Seeing a tornado tomorrow, that is very unlikely to happen. So again, that goes on the unlikely end of the spectrum, but we feel that that's more unlikely to happen than seeing snow. So it goes further towards the impossible end, but it's not quite impossible. I will feel rain tomorrow. This is Wales, so of course that's going to be fairly likely to happen. The sun will rise tomorrow. That event is not just likely to happen, that is definitely going to happen, because that is the definition of what tomorrow is. That, without fail, will happen. So that goes on the very end of the spectrum, the certain end of the spectrum. And it's not just close to the end of the spectrum, it is the end of the spectrum. You can't be more likely than that to happen. It is certain to happen. And similarly, the event, a genie will grant me wishes tomorrow, that is not going to happen. That is completely not just unlikely to happen, that is completely impossible to happen. That will never happen tomorrow. So that goes on the other end of the spectrum. And again, not just close to the end of the spectrum, that is on the end of the end of the spectrum being impossible. And the final event we look at is the first card I draw from a shuffle deck of 52 playing cards will be a black card. So is this likely to happen, unlikely to happen? Well, there are 52 cards, half of them are black, half of them are red. So we would expect half the time for this to happen. So it's 50-50. So it goes right in the middle of the spectrum, dead in the middle. Now, the field of probability is being able to apply a precise measure of likelihood to events. So we are used to, in everyday language, putting things on this sort of spectrum, but now we would like to give precise measures of how likely something is to happen. And this spectrum turns into this spectrum, a spectrum between 0 and 1. So on one end of the spectrum, 0 is the impossible events. On the other end of the spectrum is the certain events, 1. And everything else sort of happens in between these. The more likely you are, the higher the number. The less likely you are, the smaller the number. The interesting event to look at here is that event drawing a black card from a deck of 52 cards. That lies, we said it before, that lies exactly in between 0 and 1. Exactly in between impossible and certain. What number lies exactly in between those numbers? Well, a half. But remember, a half, that corresponds to what we were thinking about there. There was half the possible cards were black, half of them were red. And now we are saying this measure of likelihood is a half, and that's not a coincidence. Another way to think about this is if this was an event, if this thing was to occur lots of times, drawing a card, we would get the event, a black card, about half the time. Let's look at some more precise language around this. So we call these events random experiments. And for a random experiment, the set of all possible outcomes is called the sample space, and that's denoted by S. So for example, in our card example, drawing a card is a random experiment. The sample space is drawing a black card or drawing a red card. An event then, so drawing a black card, is a subset of the sample space. Yeah, so think back to set theory, the set of events that contains drawing a black card and the set of all possible outcomes contains drawing a black card and drawing a red card. We then use this measure I was talking about, we say that is called probability. The probability of the event E occurring is this measure of how likely it is. And we denote that by this boldface P bracket E, which denotes the event. Sometimes you won't see the boldface P, sometimes you'll just see a normal capital P. That is completely fine as well. I've separated out boldface P to normal P in this course because we saw that a normal capital P denoted power sets. So I wanted something different to denote probability, and a very common symbol for probability is this boldface P. But you will also see just a normal capital P as well. In order for us to be able to start doing things with probability, we need to know some more facts about probability. And there are some axioms of probability that exist. What is an axiom? An axiom is a fundamental truth. Okay, something we know it to be true by definition. So these are some axioms of probability that people have come up with to say from now on, every time we deal with these measure of likelihoods, we have to follow these rules. So the axioms of probability, the first one, and we've seen this before, is the probability of an event has to lie between 0 and 1. And again, that goes back to our spectrum, 0 being impossible, you can't be less likely than impossible. 1 is certain, you can't be more likely than certain. So this measure of likelihood must lie between 0 and 1. The second axiom is that the probability of the sample space is 1. So the probability of something happening that we have said is in the set of possible outcomes is 1. At least one of the possible things is certain to happen. And the third axiom is that if we have two events, so event A and event B, EA, EB, and if their intersection is the empty set, so what does that mean? It means that these two events can't happen at the same time. If the intersection of these two events is the empty set, then the probability of their union is the sum of their probabilities. So the probability of either event EA happening or event EB happening or both is equal to the probability of EA happening plus the probability of EB happening. Because we don't have to consider the both because the intersection is empty. A corollary of this is that the probability of the empty set is 0. So something has to occur. We have some tools that help us calculate these measures of likelihood, calculate probabilities, and one of the first most fundamental ones is something called the equally likely principle. What does this mean? If all the elements of the sample space are equally likely to happen, then the probability of an event E occurring is the size of the event E divided by the size of the sample space. So that is, how many events are we interested in divided by how many events can occur. We look at some examples of that now. Okay, I have two questions here. So the first question is asking, what is the probability of getting a 2 when rolling a fair-sided die? Well, for a fair-sided die, what is the set of all outcomes? The set of all outcomes is we can get a 1, 2, 3, 4, 5 or a 6. What is the set event getting a 2? Well, only one of those outcomes will be in that set. So the event we care about is the set of the outcome 2. That's the only outcome we care about. So what is the probability of event E occurring? That is the size of event E divided by the size of the sample space. And in this case, that's 1 divided by 6. So the probability of getting a 2 when rolling a fair-sided die is a 1/6. Let's look at the second example. What is the probability of drawing a club from a deck of 52 cards? Well, what is the sample space in this case? So we could have the ace of hearts, the 2 of hearts, the 3 of hearts, and so on, and there's all 52 cards there. What is the event that we care about? That's any of the clubs. So the ace of clubs, the 2 of clubs, and so on. What is the probability of that event occurring? So that is going to be the size of E over the size of S. How many events are there in E? So how many different clubs are there? There are 13 clubs in a deck of 52 cards. And how many outcomes are there altogether? What is the size of the sample space? There are 52 outcomes altogether, 52 cards we can choose from. And so this simplifies to a quarter. The probability of drawing a club from a deck of 52 cards is a quarter. Now, the equally likely principle doesn't apply to every possible set of events. It applied here, it applied to rolling a die, and it applied to drawing a card from a deck of 52 cards because, as the name says, because each outcome is equally likely to happen. And we have a feel for that. But that's, of course, not always the case. As an extreme example, what is the probability that I will see a dinosaur tomorrow? The sample space is I will either see a dinosaur or not. The event I care about is the set of I will see a dinosaur. So the probability that I will see a dinosaur is 1 over 2. I am not 50-50 likely to see a dinosaur tomorrow. So the events seeing a dinosaur and not seeing a dinosaur are not equally likely. That's an extreme case, but there are plenty of other cases where things seem equally likely and they're not. So it's up to us to be able to determine that before we can start using this technique.